plus V, that is your energy operator, or as we're now calling it, the Hamiltonian operator, or just in the context of quantum mechanics, you just tend to talk about the Hamiltonian, right? But we're talking about operators, so the Hamiltonian operator. So you can rewrite your Schrödinger equation, you know, the full form with spatial and time dependence. You can write it this way, right? Because this you know, the del squared plus V is just the Hamiltonian operator, so h hat. So you can rewrite your Schrödinger equation as h hat equals I h bar d psi dt. Right? So I put a rectangle around. That's really important. So we're now writing quantum mechanics, you know, Schrödinger equation, very important well, approach, I suppose, a very important component of quantum mechanics. We've now rewritten the Schrödinger equation in terms of operators, right? In this form. Okay, now trumpet roll, da-da, 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 da-da. Here we come to the big idea that I was alluding to at the beginning of this session, and it's the following. Have a look at this. This is an Eigen equation. Okay, you have an operator, you have your Eigen function, and you have an eigenvalue. That, you know, that format: operator, Eigen function, eigenvalue, eigenfunction, the same. These two are the same. That format works when your operator here is concerned with the observable energy. Okay, so these here, the eigenvalues, are allowed energies. They you know, discrete, quantized, allowed energies in your quantum system, right? And these are your kets, these are your eigenstates, your solutions, they're your wave functions, if you like, to your quantum system. So we've been doing this for energy, and now comes the big question, you know, trumpet roll. This kind of thinking, this thinking as an Eigen equation, can you generalize that to other observables? Right? That's the critical question, and the answer is yes. Otherwise, why would I be mentioning it? But you know, it's a really big idea. Okay, this way of thinking using Eigen equations. We've done it here when the observable is energy, but using the Eigen equation for other observables, is that valid? Does it work? You know, that's a big hypothesis, and we will show as chapters pass. You know, it'll take quite a bit of time, but this really big idea that Eigen equations are valid for other observables, right? Like position, momentum, angular momentum, energy, which we've done, and spin, and so on. So, like next chapter. Chapter 7 will be about angular momentum and spin. Right? So we'll have two more observables that that use this kind of Eigen equation type thinking. Right? So it's a really big idea, a really important idea. Okay. So that's what I've been saying. So let me sort of summarize it now. I'll sort of spell it out more explicitly. Let's assume that this Eigen equation idea, that it is valid for other observables. What does that mean? What it means is, well, you'll have an operator for each observable. Now, for the observable, you know, remember, observable just means a measurable physical quantity, like energy, right? So you'll have for each observable, you'll have a corresponding operator, right? You'll have your kets or solutions to your Eigen functions, which are solutions to your Eigen equation. you'll have eigenvalues here, and those eigenvalues, and here's where the physics comes in, those eigenvalues will be the allowed quantized values to the system you're talking about. For example, say your operator here, say the observable is angular momentum. Now, I haven't done it yet, I'm jumping ahead a little, but imagine this operator here is your angular momentum operator. And your eigenfunctions here would then be solutions to that eigenequation. But what's really characteristic is here, these eigenvalues will be your allowed, discrete, quantized values of your angular momentum, right? So then, in a sense, by solving an eigenequation, you get the allowed values here for your observable, right? That's what I just said is really significant, right? So you can solve an eigenequation, and the eigenvalues become your allowed values that you measure when you measure the observable. Yeah? And it's true for angular momentum, position, spin, energy, and so on, right? It's a really core, basic, important idea, right? Okay, so that's sort of what I've been saying. Now, in a sense, it's a postulate. You just assume it's true. And why do you assume it's true? Well, because it keeps popping up again and again, and it seems to work. Each time it works. You know, we've only done a few. We've done well, effectively energy. Certainly done it for energy, and it works for energy. Next chapter, you'll see it working for angular momentum. You'll see it working next chapter also for spin. Spin is just like an intrinsic angular momentum of a particle, like spinning on its own axis, sort of thing. So it keeps popping up. So you generalize. You say, oh, so well, maybe for every observable, you know, some physical measurable quantity. Maybe every observable has its corresponding operator. So you need to find what that operator is, and that's not obvious. But let's assume it can be done, and hence you create an eigenequation for that operator. You find the solutions, and that eigenequation will give you eigenvalues, and those eigenvalues should, you know, if this hypothesis, this postulate is correct, these eigenvalues should give you the allowed values when you actually do the measurement of that observable, right? Now, that's a hypothesis, if you like. It's a postulate. You just assume it's true, and as confirmation, you know, verification that it's true, well, experiment. You know, you just go to the lab and you actually see. You just see by observation, by experimental observation, that the predicted eigenvalues here, you know, in this case it's energy, but you know, if that were angular momentum, you'd have allowed angular momentum values here. If that were the spin operator, you'd have allowed spin values, and so on. Okay, so you go to the lab and you actually measure what these are, these discrete, these quantized values are of your operator, of your observable. Remember, we're heading towards the idea that each observable has its corresponding operator. Right? That, you know, I'm jumping ahead a bit again, but we're heading that way, right? And for each observable, there'll be an operator, and you remember that because we'll definitely come back to it. It's another one of these big ideas for quantum mechanics. Okay. So anyway, to confirm this idea that there's an eigenequation for each observable, and hence an operator for each observable, a set of allowed measured values for each observable and corresponding kets or states for each observable, a set of those as well. All right, that idea is confirmed ultimately just by experiment, right? The experimental physicists show us that it's correct. All right, now in the next session, I'll talk a little bit about some of the properties that these quantum mechanical operators have, and also a bit about certain properties that these Eigen values also have. But that's for next session.